Hello student, most welcome to Dr. Acharya Academy. Today I'll discuss the hybridization involving d-orbitals. Today's class number is 083. The elements belongs to the third period. These elements contain the d orbitals in addition to s and p orbitals we know. The energy of these 3d orbitals, it is comparable to the 3s and 3p orbitals because all orbitals belongs to the same principal quantum number 3. So the energy of 3d orbitals are also comparable with the energy of 4s and 4p orbitals. And the consequence is that the hybridization is possible either with 3s, 3p and 3d orbitals or 3d, 4s and 4p orbitals. There is some energy difference between 3p and 4s orbitals, so hybridization is not possible in between these orbitals involving with 3d orbitals. Some important hybridizations you can find in this table. Hybridization type, this mention is there, and how many atomic orbitals, how many different types of atomic orbitals involved with this, and what is the examples of the molecules with its shape. So I'll discuss two examples. Number one, formation of phosphorus pentachloride, which is the sp3 dehybridization, means 1 s orbitals, 3 number of p orbitals and 1 number of d orbitals involved with this. So phosphorus in ground state, its electronic configuration is 3s2, 3p3 and 3d doesn't have any electron. That means empty 3d orbitals. So when phosphorus is excited, then the electronic configuration from this 3s, one electron is jumped to the 3d orbitals, and finally you'll get sp3 d orbitals, and number of hybridized orbitals is 5, and then 1, 2, 3, 4, 5, these numbers sp3 d hybrid orbitals will form bond with the chlorine atom, sigma bond, and then for the PCl5 its electronic configuration will be like this, and these sp3d hybrid orbitals filled by electron pairs donated by 5 numbers of chlorine atoms. So these 5 orbitals, as I already discussed, is made hybridization to form the 5 numbers of sp3 hybrid orbitals, and these hybrid orbitals is directed to the 1, 2, 3, 4, 5. These 5 corners of a trigonal bipyramidal. This geometric shape is trigonal bipyramidal. Trigonal, because this position you can see is the equatorial position and this is the axial position. So in equatorial position, 3 numbers of bond is there, and in axial position, 2 number of bonds are there between P and Cl. It is a sigma bond. Some points here you have to remember for this geometry, trigonal bipyramidal geometry of phosphorus pentachloride molecules. First point, all the bond angles are not equivalent. See, this is the one bond angle and this is the one bond angle. It is not the same. So all bond angles in this geometry between P and Cl, that means Cl, P, Cl, this bond angle is not same for all bond angles. Here you can see 3 number of PCl bonds, the 1, 2 and 3. This is in one plane. And what is the angle? This Cl, PCl, this is 120. This Cl, PCl, it is the 120. And this Cl, PCl, this angle also 120 degree. Because these 3 bonds belongs to the same plane. And these bonds are called equatorial bonds. So remaining 2 bonds, this one is the above and one is the down of the plane. This is 90 degree. This is the 90 degree and this is also 90 degree. And these 2 bonds are called axial bonds. The axial bond pairs suffer more repulsive. These 2 bonds suffers more repulsive interaction from the equatorial bond pairs. See, these all are nearby of these axial bonds. So these axial bonds will be repelled by these equatorial bonds. So as the axial bond pairs suffer more repulsive interaction from the equatorial bond pairs, therefore the axial bonds have been found to be slightly longer. Is the longer, elongated, because repulsion is there. So this bond will move up further and this bond also will move down further and hence slightly weaker. And these 2 bonds are slightly weaker than the equatorial bonds. And that is why the PCl5 molecule more reactive. Now we will find another example for the sp3d2 hybridization. Example molecule is SF6, sulfur hexafluoride. And in this hybridization, 1 number of 3s orbitals, 3 numbers of 3p orbitals, and 2 numbers of 2d orbitals participates to form this type of hybridization. So sulfur, which is the central atom in ground state, its electron configuration is 3s2, 3p4, and 3d orbitals have no electron, but in excited state, these 3s orbitals, which is pair, and 1 of the 3p orbitals, which also paired, they unpaired, and these 2 electrons shifted to the each of the 3d orbitals being unpaired. And now this is the sp3d2 hybridization in excited state, and these electrons will pair with the single electrons from the F atoms. So here it is written there, these orbitals hybridized to form 6 new sp3d2 hybrid orbitals, which are projected towards the 6 corners of a regular octahedron in SF6. So this is the regular octahedron, and central is the sulfur atom, and all 6 corners of this regular octahedron occupied by fluorine atom. And these 6 sp3d2 hybrid orbitals overlap with singly occupied orbitals of fluorine atoms to form 6 numbers of SF sigma bonds. And in this way, the SF6 molecule has a regular octahedral geometry, as it is mentioned in this figure, in this shape. I hope that you understand this type of hybridization involving s, p, and d orbitals. And I've given 2 numbers of example molecules. One is phosphorus pentachloride, and another is the sulfur hexafluoride, to explain the different type of geometry for these molecules by adding different types of s, p, and d orbitals hybridization. Thank you so much for watching this class.